All right, welcome everybody. I want to quickly talk about some energy concepts and make them simple. This is mostly to get you ready for the test, which is coming up. So I want to try to take the concepts from this whole unit, focus on some of the things that are confusing people, tripping people up, and try to simplify them so you can understand them so you don't miss these. All right, the first thing is the units. And the units, we don't have very many units, but they're tricky because they use different symbols for the units. For example, meters. If you see a problem that says 20 meters, this could be an X. You could say X equals 20. Or it might be a distance. You could say distance equals 20 meters. Or it could be a height. So you might say height equals 20 meters. So if you see meters, keep in mind it could be an X, it could be a D, or it could be an H, depending on what is what. And we're going to call, it's going to be used, we're going to use a D when talking about work. So if the problem says anywhere in it work, you know we're going to use D. And if it's an H, is only if we're talking about energy. So that might be some clues for you. So we're using D for work, and we're using H for energy. All right, so keep those in mind. So if something says 20 meters, it could be an X, a D, or an H. All right, the other unit that's a little bit confusing is joules. And joules will sometimes be W for work, and it will sometimes be an E for energy. So if I say 30 joules, this could be a W, and 30 joules could also be an energy. So the keywords to look for there, I actually put right here, the keywords work, energy. So if you see work, you know the joules is work, and if you see energy, you know it's E is energy. All right, the next thing I want to look at is work. And some people still don't quite get this, but I want to make it very big, very clear. If there is no distance, work equals 0. And we did a demonstration of this where we had somebody in front of the class and they were holding jugs of water out to their sides. And they had lifting their arms up, and even though it felt like there was work, because there's no distance, there is no work. Work is 0. So if you're pushing something or pulling something and not moving, W equals 0. So maybe we need to write that down. No distance means 0, work is 0, or if not moving. All right, so no distance means W equals 0, or if it's not moving, there's no work, 0 work. So don't miss that on the test. All right, some people are still getting confused about potential energy versus kinetic energy, so I want to try to simplify this a little bit. If anything has a height, it has potential energy. If it has a height, potential energy. That's as simple as I can make it. So if you have something that's off the ground, whatever height it is, it has potential energy. That's it. There's nothing else to it. And that just means it's stored. It's stored, it's ready to fall. So anything that has a height, it's ready to fall down. It has this stored potential energy. And anything moving has kinetic energy. So if anything is moving, you automatically know, boom, it must have kinetic energy. All right? And so, like I said, I can't make that any simpler. If it has a height, potential energy. If it's moving, it has kinetic energy. And if it's both, if it has a height and it's moving, well, then it has both. It has both potential and kinetic. All right. Work and energy. We talk about work, we talk about energy. We just said they're both in joules. But why? What's the relationship? So I want to talk about this a little bit. We're going to look at this problem. How much work is needed to lift a 2-kilogram chihuahua a distance of 4 meters? How much work is needed to lift a 2-kilogram chihuahua a distance of 4 meters? All right, so I see how much work, W equals question mark. I see 4 meters. And as I said before, that could be an X, it could be a D, it could be an H, but because this is work, it must be a D. All right? And I do have an equation for work, which is work equals force times distance. And I have a distance is 4. And I do have this piece of information, which I didn't forget about, this 2 kilograms. This 2 kilograms is a mass. So what this means is I need this force. And the force, according to our other equation on the wall, is mg. So our force is the mass times gravity, which is 20 newtons. I can plug this in, and I get a work of 80 joules. All right? So it takes 80 joules to lift this chihuahua to this height. That's how much work. If I'm physically picking it off the ground and lifting it 4 meters, it would take 80 joules of work. That's how hard I have to work to get it to lift up there. Okay, 80 joules. So how does this relate to energy? This is something we haven't really talked about yet, so that's why I want to do it now. I want to kind of explain a little bit. All right, so this question, what is the potential energy of the same chihuahua, 2 kilograms, and it has a height of 4 meters? Same height. Same chihuahua, same height, everything's the same. What's the potential energy here? Well, potential energy is equal to mgh. So it's equal to the mass times the gravity times the height. And I get 80 joules. You'll see these answers are the same, right? 80 joules, 80 joules. So when I lift this chihuahua off the ground and I raise it up, I did 80 joules of work to lift it there. That means it now has 80 joules of potential energy. That's how much energy it now has. So even if I'm not working anymore and I'm holding it stationary, I'm not doing work anymore, but I already gave it, that work that I did went to the potential energy. So that's where that potential energy came from. We can't just create energy out of nowhere. It came from that work. So when I did the work to lift it, that's where that potential energy is coming from. And you can see it matches perfectly. All right? And if we have the same chihuahua, 2 kilogram chihuahua, and we drop it from a height of 4 meters, what's the kinetic energy right before it hits the ground? So if I'm finding the kinetic energy, we have this equation. So we have energy equals 1/2 the mass times velocity squared. I didn't give us the velocity. Actually, I don't need this though. I don't need this because if I lifted it and it had 80 joules at the top, it's going to have how many at the bottom? 80 joules. So the kinetic energy is also going to equal 80 joules. Let's rewrite it like this. So it took 80 joules to lift it. That's how much work it took. At the top, it's sitting there, stored 80 joules. And when I drop it right at the bottom, it has 80 joules. Energy is always conserved, not created, not destroyed. And this kind of shows you how these three things are tied. How the work is tied in with the potential energy, and it's tied into the kinetic energy. All right, so let's take another example. Let's look at this roller coaster. So this roller coaster, let's say it starts way over here on the left. Let's say it starts way over here. And in order to get up the hill, it needs electricity to power it, to lift it that high. So it is doing work to lift it up to the top, up here. Once it's at the top, it now has potential energy. It is stored at the top. And if it took 500 joules of work to get it to the top, at the top it would have 500 joules. As it goes down, once it hits this point here at the bottom, it's moving. It would have kinetic energy, and it would be 500 joules. And as it comes up, maybe at this point right here, it has a height. So it does have potential energy. It's moving. It has kinetic energy, so it has both potential and kinetic. But the total energy, 500 joules. And at any point along here, I can look at it here, or here, or here. Any point, it's always going to be 500 joules. But it changes. It changes from potential to kinetic to potential. Let's look at another example. Here's a pendulum. Our pendulum is going to be swinging. So it's going to swing down this way, down to the bottom, and then it's going to start going back up again. All right? And so let's say our potential energy up here is 8 joules. And it would have 0 kinetic. It's not moving yet. We're holding it up here at the top. As we lower it, when it gets down to number 2 here, it lost height. So it might only be at 3 joules of potential. But it's moving. So it would have 5 joules of kinetic for a total of 8, which is what we had at the beginning. And as it gets down to the bottom, number 3 here, it's at the bottom. It has no height, no potential. So all of it would be kinetic. So you can see again, it's 8. And at number 4 here, it's going up. So it has height, maybe 3 joules. If it has 3 joules, the kinetic energy would be 5 joules again. This would have to be this true because it adds up to 8. And at the top again, number 5, it's all stored and it's not moving. It'd be 0. So you can see it's always 8, but it just changes. Potential to kinetic to potential. All right. For our lab, we had a cart. The cart was on an incline. And we measured the potential energy and we measured the kinetic energy. And you should have got some data that said something like this. If our potential energy at the top is 0.6 joules, our kinetic that we measured at the bottom might have been 0.4 joules. And everybody, every single person in this class had a bigger number for their potential energy at the top than the kinetic energy at the bottom. Every single person should have had a higher potential energy than kinetic energy. Because why? Why did we lose energy to begin with? Shouldn't both of these numbers be the same? Yes, they should. So we have a missing 0.2 joules. We know it can't be destroyed, so where did it go? It went somewhere. So what happened is we had our potential, and it turned into something. It should turn into kinetic, right? But in reality, we actually turned it into kinetic, and we turned it into some other things. For one, we had friction. The wheels were rubbing against the track, and we know from friction when things rub, we get heat. So some of that 0.2 missing energy went into heat. And some of that energy also went into air resistance. And some of it went into sound. Because we heard the car going down the track. So if we looked at these numbers, this might be 0.6. And I said this would have to be equal to 0.4, but it wasn't, right? The potential did not equal the kinetic. But if we add the heat, maybe it was 0.1, and we add the air resistance, maybe it was 0.05, and we added the sound. If we add all of those sources, it would equal the same. So energy is conserved, but in our labs, the kinetic wasn't equal to the potential because some of that potential energy was not converted to kinetic. Some of that potential energy was converted to heat, to air resistance, to sound. So that's where that extra energy went. Last slide. Suicidal squirrel. I want to talk about this. This was on the problem set from the lab. If the potential energy of a squirrel on a tree branch is 1,000 joules, what is his kinetic energy halfway down? So this was one of the questions, and so I want to take a quick look at this because people were asking me about it. How do you draw a squirrel? They kind of have big bushy tails, right? Okay, so here's the squirrel. He's on a tree branch, and he has 1,000 joules. Okay, as he falls, let's put him down here. Bushy tail. Okay, as he falls, he lost potential energy. It is less. And if he is halfway down, I would say he has half the potential energy. But the question is asking, what is his kinetic energy? If he started with 1,000 and now he has 500 potential, he should have 500 kinetic. Because 500 plus 500, it needs to equal the 1,000. Those need to be equal to each other. So I hope that makes sense. I hope these points clarified some things for you. I hope it simplified it a little bit. I hope it makes more sense. If you have any questions, please email me or come by and see me, and I'll be happy to talk to you more about this. To make it clear before the test, I want to see everyone's grades go up, up, up. And so the best way to do that is if you're confused, ask questions, get help, so you'll do well on the test. All right, thanks for watching.